So before we get rolling, we just have to think about this shape we're going to run into. Most of the time we call this a washer. You can think of it as like shaped like a CD. It's two concentric circles. One is like the hole in the middle and then a solid shape around, and this has thickness. So if I wanted to find the volume, I would need pi times the big radius squared times the height. And I could subtract out the volume of the hole in the middle, which would be pi, we usually call it little r squared, times the height. There are ways you could use the distributive property to rewrite this expression, but that's all you need is some way to think about how to find the volume of a slice that's kind of like the slices from the last section, kind of like a disk, except it has a hole in the middle. So this is the volume of the hole, W-H-O-L-E, as if it had no space in the middle. You could subtract away the volume of the hole, H-O-L-E. This is the one last thing we have to consider when we talk about finding volumes of solids by slicing. What if the region that we're revolving around an axis doesn't actually bump all the way up against that axis? When you revolve your shape around, you're going to end up with some kind of hole in the middle. So I chose this problem not because it's that interesting or special, but because the book publishes this nice picture for us to see. So if we call this region, I don't know, A, and it's already shaded in, now I want to highlight my axis of revolution. I've been asked to revolve it around the x-axis. But look at all that space in between my red line and this shaded shape. So when this revolves, I'm going to have a solid, but it's going to have space in the middle. So the book gives us this picture, which is very helpful. So you can think about, I draw my slices in green, they drew their slice in pink. But you get the idea. If you take a slice, it's going to be like this big pink disc, but there's going to be a hole in the middle. So that's where we're going to have to use that expression for volume we just wrote before, which is we're going to find the volume of the hole, W-H-O-L-E, and then subtract out the volume of the hole, where each slice is what we call a washer, which is a disc with space in the middle. All right, so I'm going to keep going with my regular plan, which is I've drawn in my axis of revolution. I'm going to sketch the reflection. Oops, let's do this. That wasn't awesome. I could probably do better. Here's my axis of revolution. Here's my solid, my reflection. Ends up looking like a fish mouth. All right, so you can imagine revolving that around, you get the picture that we just saw, which looked nice in 3D for us. Here I'm going to suggest you draw two slices. So I'm going to draw one slice. That means me starting. Oh, so I suggested two slices. Think about drawing a slice that represents the whole, W-H-O-L-E. And we'll draw a second slice that kind of shows us what a slice of the whole, H-O-L-E, would look like. So inconvenient that those are homonyms. So I'm going to draw, starting my pen at the axis of revolution, I'm going to draw toward the picture that I have equations for. I'm going to draw toward the outermost first. So I want this to be the picture of the outside shape. And now I'm going to use my blue pen and try to draw in that radius. So I'm going to go from the axis of revolution to the edge of that circle. So in textbooks, it's pretty common for us to refer to that blue line segment I drew as capital R, meaning the bigger radius of the two radii that we need in this problem. Again, that's the radius like of the outside edge of the shape that we're going to create by this revolution process. We're going to use little r to stand for the radius of the hole in the middle of the shape. I'm going to put B out of the way here. So I'm going to write that we decided that capital R, let's see if we can decide. It's a vertical line segment, which means if I want to find its distance, I'm going to subtract top y minus bottom y. Well, the top y seems to have bumped into that upper curve there. I know when I'm talking about sine and cosine, this is going to be the cosine curve. So R is going to be cosine of x minus the bottom of my vertical line segment is the x-axis, which is y equals 0. I could write cosine x minus 0, but that just complicates my life. So my capital R is going to be cosine of x. Now I'm going to draw in a smaller slice. I have this other green, see if that helps. I'm going to start my axis of revolution, draw toward the inside function. I'm going to make my blue radius. Always starts at the axis of revolution and draws toward the edge of the circle, ideally toward a function that you have a function, like a function rule for. So my little r, I'll do that in light blue. Also a vertical line segment. To find its distance, I'm going to subtract top y minus bottom y. Well, the top y, the top of my line segment bumped into sine of x. My bottom of my line segment bumped into the same x-axis, y equals 0. So here's my expression for capital R, my expression for little r. So you might like to write, well, I'm going to write 2 integrals. Your textbook sometimes writes 1 integral. You're certainly welcome to write 1 integral. But I find that this helps students stay focused. So I'm going to imagine that I didn't have a hole in the middle of my shape. If it were solid, the volume would be pi. Took vertical slices, so the change in thickness is a very small change in x. It's going to be dx then. It's going to be r squared, and that has to be those have to be x values. So x is here. What are my x limits? The left limit is x equals 0. The right limit is where sine and cosine intersect. Can you think of any angle you could take the sine of and you could take the cosine of and get that same answer? I hope you can think of that. That's pi over 4. That's supposed to be a pi. It didn't really look like a pi. It looked like a k. That's pi over 4 is my upper limit. And my radius, capital R, cosine of x. That's if there were no space in the middle of my shape. It would have volume pi times the cosine of x squared dx, integrated from 0 to pi over 4. Now I'm going to subtract out the volume of the hole. That's also going to have a pi out front. Same limits. If you ever had different limits here, something went really wrong. And then here, the volume of the hole in the middle is going to come from slices whose radii have sine of x as the top curve and y equals 0 as the bottom curve. So it's going to be sine x squared. Final answer.